Hello, this is Dr. Phil Rosenkrantz again for EGR 403 Online. Today we're talking about interest and equivalence. This is presentation number 5. If you'll go to slide number 2, we'll look at our big picture again, and we'll see that we're in chapter 3 of our text, and we're talking about the concepts related to the time value of money. Chapters 3 and 4 work with the formulas and the methods for calculating the numbers we're going to be using for our analysis methods later on. So this is a very important chapter, chapters 3 and 4. If you don't understand those, you're going to have difficulty throughout the rest of the course. The concepts aren't very difficult, but they do require that you invest some time to master them. Let's go to slide number 3. Put a little context on what we're doing here. Referring to economic decision making, if we're making a decision where we're trying to deal with immediate needs and there's not a lot of time involved, then our big concerns are things like how much are we spending and what are the tax consequences. And we'll be talking about taxes in some of our later chapters. But where our economic decision occurs over a period of time, in other words, we're talking about a project with a life cycle of 2, 3, 4 years, 10 years, 100 years, then the amount of the expenditure and taxes are certainly concerns. But interest and inflation become big concerns, if not the biggest concerns. So keep that in mind. We deal with cash flows in making our computations, and just a couple basic comments here. We look at costs, money that we pay out or disbursements, most of the time as a negative number. You'll see a few exceptions to that later on. And we treat benefits or money that comes in as receipts or as a positive number. And so we'll be making some pictures of that later on. We call them cash flow diagrams. Those of you that have had statics remember dealing with free body diagrams, and you used vectors there, but here we're going to use just up and down arrows to relate our cash flows. But anyway, just wanted to mention this right now. Let's go to slide number 5. The time value of money is what this course is really all about. Sometimes you'll hear mention of discounted cash flow. That's the same concept. Money has value, and we can rent it or lease it, and when we do that, the payment for that service is called interest. So if you put $100 in a bank at 9% interest for one time period, you'll receive back your original $100 plus $9 interest, and that's the $9. That $9 was for them being allowed to use your money for that time period. Now, $9 or 9% would be very high right now in a bank, but this is just an example. Go to slide number 6. There used to be a concept you'd hear about all the time called simple interest. You may have learned simple interest in the junior high school or something like that. And that's where interest is computed only on the original sum or original principal. And principal is a word you'll hear over and over again, referring to the initial sum that was invested. With simple interest, the formula is that the interest equals the principal times the interest rate times the number of periods. And you can see an example there. And so just multiplying those three things together gives you the simple interest. In this case, if you have a principal of $1,000 with an interest rate of 10% or 0.10 and have 2 time periods, then the interest is $200. Let's go to slide number 7. So the future value of a loan based on simple interest would be the interest plus the original principal borrowed. And so you can see a formula there where those are added together, and we get a future value of $1,200. That's based on simple interest, but we don't use simple interest today for a number of reasons, and but needed to put that in perspective for an example later on. What we use today is a concept called compound interest. Compound interest is what is used throughout the business world today, and compound interest is computed on the original unpaid debt, the principal, as well as any unpaid interest. Let me illustrate that with an example. Let's suppose in year one, you have the same example as before. Principal is $1,000 and you have a 10% interest rate. And so the interest for the first year is $100. But unlike the simple interest example, what we're going to do is we're going to add any unpaid interest for the time period to the principal and get a new principal for the next time period. In this case, we'll add the $100 since we haven't paid it yet, but we owe it. We're going to add that to the $1,000 of first year principal, and we get $1,100 is our new principal for the second year. So our second year's interest will be based on that. You can see that $1,100 times 10% is $110. So if we add our first and second year's interest earned together, 100 plus 110, we get $210. Now you'll notice that that $210 is $10 more than with the simple interest formula that we used. Let's go to slide number 9. If we look at what we just did mathematically, we could see that the future value of those 2 years with compounding was equal to the principal plus the first year's interest plus the second year's interest. If we multiply out the formulas there, and if we factor out the principal P and then complete the square, we end up with a formula that says the future value is equal to $1,000 times 1 plus 0.10 raised to the second power, or squared. And that gives us the $1,210 that we had. Now, in general, if we extrapolate that and we go to longer periods, instead of 2 years, we go to 3, 4, or up to n periods, we actually can derive a general formula, and it's in your book if you want to look at it, where the future value is equal to the present value times 1 plus I to the nth power. And the interest earned would be that minus the principal. And that formula there is a very fundamental or foundational formula, and it shows the effect of compounding. Let's look at slide number 10 and see what happens over a long period of time. If you had loaned your friend that $1,000, say, for a short period of time, the difference between simple and compound interest is negligible. For example, for a 1-year loan, it would be the same, just $100 of interest. For a 2-year loan, the difference between simple interest and compounding would only be $10. So that's not very much. But let's go down the table to where we're talking about a 40-year loan. If we calculated the simple interest for 40 years, $100 a year for 40 years, it's $4,000. Add the principal to that. That's $5,000 total. That would be the loan payback based on simple interest. But if you do compounding, you'll see that the right column for the future value based on compounding is $45,259. So there's over a $40,000 difference when compounding is taken into effect. So you can see the power of compounding and why it's really important in the financial world today. Let's go to slide number 11. I'm going to slightly change pace a little, talk about different types of interest rates. This is a terminology issue and a definition issue, and it's real important that you master these interest rate definitions, because if you don't, you really struggle in being able to understand problems and work them out and perform well on any quizzes. Nominal and effective interest rates are annual interest rates, and periodic interest rate, which I'll mention here in a moment, can be an annual interest rate, or it could be less than annual. So let's go through these. The nominal interest rate, R, is the annual interest rate without considering the effect of any compounding. So we could say a nominal interest rate is 12%. The interest rate per period, we use the letter I for that. That's what we use in our course. It is the nominal interest rate, R, divided by the number of compounding periods in a year. So for example, if we have a nominal interest rate of 12% and we have monthly compounding, well, there are 12 months in a year, so our periodic interest rate would be 1%. So I is equal to 1%. The effective interest rate is an annual rate. We see in our book the notation I with a subscript effective, or EFF. But the effective interest rate is known in the business world as the annual percentage rate, APR. And what this is, it's an annual incentive rate, interest rate, taking into account the effect of compounding during the year. What we'll show later on, for example, is that if you have a 12% nominal interest rate, but you have monthly compounding, that you effectively have a 12.68% effective interest rate. Okay, let's go to slide number 12. Just to clarify some of these numbers, we use I to represent the periodic interest rate, R for the nominal interest rate, and that's always an annual rate. The number of compounding periods in a year, we use the variable M. And so R equals I times M, or we can rearrange that, and I equals R over M. And here's a few examples. If we're talking about annual compounding period, then we only have one compounding period per year. And so the interest rate I equals the nominal interest rate R. So that was simple. But if we have quarterly compounding, we have 4 compounding periods in a year. And so our interest rate is 12 divided by 4, or 3%, 0.03. If we have monthly compounding, then we have 12 interest periods in a year. So the periodic interest rate is 0.01, as we mentioned on a previous slide. So I hope you find this to be a fairly simple concept, but don't mix up R, the nominal interest rate, I, the periodic interest rate, and I effective, the effective interest rate. We have a formula for computing effective interest. I have a tendency to cover this in Chapter 3 lecture, even though in our text it's in Chapter 4. And I just think it fits in here. The effective interest rate takes into effect the compounding during the year, if any. And here's our formula for it. I effective equals 1 plus I raised to the m power minus 1. If you're not given the periodic interest rate I, but you're given the nominal interest rate and the number of compounding periods in a year, then you can divide R over M and get I. So let's take our example that we've already used with 12% interest rate and 12 compounding periods in a year, monthly compounding. And if we plug and crank, we find that the effective interest rate is 0.1268 or 12.68%. So the effect of compounding is in reality an extra 0.68%. Now that may not seem like very much, but if you consider that that compounds year after year, period after period, that can add up to be quite a bit of money. And so if you're borrowing money and they tell you that the interest is compounded monthly, you know that it's going to be a little bit more than if it was compounded, say, quarterly or semi-annually. Now, some of you actually have credit cards that compound daily, and so that can jack up the true interest just a little bit more. And if you look at your credit card statement, you'll actually find where they tell you what the daily interest rate is that they use for compounding. Okay, let's go to slide 14. To further illustrate some of what we're talking about here and to kind of set up what we call the concept of equivalence, I want to expose you to 4 different ways here that you could, say, repay a loan. And then I'm going to use these 4 different ways to make a point and illustrate some things. Plan 1 would be where you borrow money and you pay the principal back in equal chunks. Just divide the amount you're paying back by how many years, let's say. And then you pay interest on the unpaid balance based on your interest rate. If you do that, the interest declines over the period of time. The second way, the second plan, would be to pay all the principal back at the end of the loan, but during the loan, just pay interest each quarter, or rather each period, on what the unpaid balance is. In that case, the interest paid or earned is constant. Plan 3 would be equal installments, where you make the same payment every period, and at the end, you've paid off the loan. In reality, even though you've made the same payment each period, the interest paid is declining. Now, if you go and buy a car or buy a home, then this is the plan you're doing. You're making equal payments, and the principal and interest are all lumped together into that equal payment. And finally, plan number 4 is where you pay everything at the end of the loan, and so there's a lot of compounding going on, and the interest keeps increasing because of that compounding. So let's look at these 4 plans in detail. I think this will be helpful. Let's go to slide 15. Plan 1, equal principal payments. So if we say borrowed $5,000 and we're going to pay it back in 5 years and the interest rate is 10%, then in year 1 we have a balance of $5,000. We're going to pay $1,000 on the principal. We owe $500 in interest, don't we? Because 10% of $5,000 is $500. So our payment is going to be $1,500. Again, that's $1,000 to pay on the principal and $500 for interest owed. And then each year, because we've paid off some of the principal, the new balance is lowered, and so the interest owed each successive year is a little less. And without going through each one of those line by line, you can see that the payment drops. And if we add those 5 payments together, we see that we've paid out over the 5 years a total of $6,500. $5,000 of that went toward repaying the principal, and $1,500 was the interest charge for renting that money. Okay, let's go through the next ones, but maybe not as quite as slow. Plan 2 is where we don't pay any of the principal back until the end, but we're making interest payments. Well, because our balance stays high at $5,000, the annual interest is 10% of that, or $500 a year. So we make payments of $500 a year for the first 4 years, and then the last year we have principal and interest of $5,500. The total that we pay over the life of this loan is $7,500. You'll notice that there's $1,000 more than the previous year, or the previous plan, Plan 1. Let's go to slide number 17, Plan number 3. Now we're going to make 5 annual equal payments. Now, I'm not going to go through how we got those numbers right now. That's in Chapter 4. But those would be equal payments of $1,319. What's worth noting here is that we have the principal and interest columns show changing numbers there. Let me show you how those are calculated, because this is the example I'm going to give you of how to put together a payment schedule and allow you to calculate principal and interest payments. So let's look at the first year. We know that 10% of $5,000 is $500. So our interest charge is computed first, and that's $500. So all the rest of our monthly payment, or rather our annual payment, goes to principal. So we subtract $500 from the $1,319 to find out how much is left over to go to principal. In this case, $819 is how much of our payment went to principal. Well, since we paid that much on principal, our next year's starting balance is going to be $5,000 minus that, or $4,181. So our interest in year 2 is going to be 10% of that, which is $418.10. The rest of my monthly or annual payment will go to the principal. That would be $900.90. So do you see what's happening here? We compute our interest first. The rest of the payment goes to principal, and it reduces the next year's principal balance. And what happens is, when we finally get down to the end, everything zeroes out. We've paid off the loan, and if you add up the 5 annual payments, you get a total amount that we paid for the loan of $65.95. Plan 4 is where we pay everything at the end, and you can see what the numbers are there, and it's simply adding the interest from each year earned onto the principal for the next year, because we haven't paid that interest off, so it becomes part of next year's principal. Another good example of compounding. Let's go to slide number 19. So let's ask this question: which plan would you choose? The 4 plans had different totals: $6,500, $7,500, $6,595, and then $8,052. Which one of those would you choose? Which one's the best? Well, usually when I ask this in class, and I can see people raising hands and answering that, the most common answer I get is that Plan 1 is better because that had the lower total amount, $6,500. Well, the answer is that, first of all, these 4 amounts are all equivalent. I'm going to mention that on the next slide, what that means. So from a time value of money, none of these are better than the other. But let me rephrase my question about which one was best. What if the only thing you could do with your money, if you weren't paying off this loan, was you could put it in a bank passbook savings account for 2.5%. If that's what you were going to do with your money that you weren't going to use to pay off your debts, then plan 1 would be the better one, because you would be avoiding as much interest at 10% as you could by paying off the principal as fast as you could. So plan 1 would be better. But what if I changed the question and I said that you had an investment that you could make that would give you 20% return on your money? It would give you a 20% interest rate. Now, which plan is best? Now plan 4 is best, because now you have that $5,000 to invest for the longest period of time, and you'll be making 20% on that, and you'll be happy to pay 10% for having borrowed that money. So these are all equivalent, and which one is best is based on what you can do with your money if you're not having it involved with this 10% interest rate. So let's go to slide number 20 and talk more about equivalence, and mention again that if you've used the same interest rate to make all of your calculations for compounding and interest, then the cash flows are equivalent. And that's a concept that you need to understand in this course, concept of equivalence. So if I have $100 today, that's equivalent to a certain amount in the future at 10%, if 10% is the interest rate that I'm using. Let's go to slide number 21. To further illustrate this concept, suppose you're given the choice of these two plans, and you're going to make a payment based on one of these two plans. Which one would you choose? Well, it's pretty hard to just look at those numbers and know which one's best, because you've got the time value of money mixed in to those two series of cash flows spread out over 5 years. So in order to make an analysis, what we need to do is alter those cash flows so that we get two numbers that we can compare. We use the concept of equivalence to do that. So for example, we might find a single value for plan 1, some number, or a single number for plan 2, but at the same interest rate, and then compare those two numbers to decide which is the best investment or the best payment plan. Let's go to slide number 23 and point out that in this course, what we're going to be doing exactly that. We're going to be comparing alternatives and choices by finding equivalent values and then comparing those equivalent values. And for example, the technique we use that we learn about in Chapter 5 is called present worth analysis. In Chapter 5, we find the equivalent value of all the cash flows at time 0, and then we compare those. In Chapter 6, we use annual worth analysis, where we find an equivalent annual worth of all of our cash flows and we compare those. Now you might start asking at this point, why do we have those two different techniques? The reason is because we have different types of situations that just lend themselves to different types of analysis based on what the data is. If you're comparing just two simple pieces of equipment, machine A and machine B, present worth analysis is very good. But let's say that you're comparing two leases, or the purchase of or rent of some facilities. Then looking at everything from an annual worth basis might make more sense because it kind of flows better with budgets and looking at things on a year-to-year basis. In chapters 7 and 8, we talk about rate of return analysis. Here we're comparing interest rates for each alternative to a minimum value that we would accept. So our single number there is an interest rate. Chapter 9, we look at future worth analysis. Sometimes what's important to us is comparing what something will be worth at some point in the future. For example, if you're comparing investments or retirement options, you might be concerned about what the future worth is at your retirement age. And finally, benefit cost ratio analysis is covered in chapter 9. We take some equivalent values, different ones, and we form some ratios, and we use that technique and use ratios because they lend themselves to handling massive amounts of data efficiently. Let's go to slide number 24. Talk about interest formulas. We're starting out talking about single payment formulas. That's what chapter 3 is all about, just the single payment formulas. And the four variables we're concerned with are the interest, I, that's interest rate per period, N, the number of interest periods in our project or in our investment. Now don't confuse N with M. I'm going to repeat that. Don't confuse N, the number of interest periods in your project, with M, the number of interest periods in 1 year. They're not the same unless the project you're dealing with has a 1-year useful life. Also, we use the single letter capital P to represent the present sum of money. That's sometimes called the principal. It's sometimes called present worth. It's sometimes called present value or PV. I mention PV because some of you have calculators that actually have buttons on them for calculating PV. That's the same as RP. Then F, the future sum of money, or future worth, or future value. If you know any of the three of those four variables, then you can find the other one. For example, let's say that we're given a future value, what something is going to be worth after n time periods, and we have present value, what our investment was, and then n, the number of periods involved. We can find out what interest rate makes those two cash flows equivalent, and we call that interest rate often the rate of return, or ROR. We have our future worth formula, F equals P times 1 plus I to the n. If we solve that algebraically for I, the interest rate, we do get a formula for that. So if we need to, we can solve that formula to find a rate of return for this simple situation where we have single payments. Let's move to slide number 26. We also have a notation methodology that we use for this course, and it leads us to being able to solve for, say, the future value given P, N, and I with several different approaches. One way you can solve the problem is with the formula in a calculator. Another way is to use factors and functional notation in the tables in the back of the book. Third way is to use the financial functions available on Excel spreadsheets. And finally, another way is that you have the same financial functions, many of you, on your calculators. You may or may not be aware of that, but most of the graphing calculators have some sort of financial function module or functions available. Now in this course here, we are not going to use the formulas very much. We are going to be using the factor notation and the tables in the back of the book, and we're going to be using Excel. If you find yourself wanting to use the formulas, then you need to hold off, and unless I've specifically asked you to use a formula, you should be using the functional notation or the Excel spreadsheet. Okay, I mentioned that because I have some students that they just love to use formulas. They program them into their calculators, but what you'll find is that those only work for the simplest problems. But the functional notation and the spreadsheets, you can do complex problems very quickly. Okay, let's move to slide number 27. We also use cash flow diagrams in our analysis because they help us to organize and observe the data. And like I mentioned earlier, we have disbursements and we have receipts. And so typically our disbursements or costs would be a down arrow in a cash flow diagram. And our income, money in, would be an up arrow. We also show on our cash flow diagrams the number of time periods. For example, on slide 27, it says n equals 4. And then if we have an unknown we're solving for, like in this case, maybe it's the interest rate, the periodic interest rate, we'd say I equals question mark. Now you'll notice in this cash flow diagram example, we don't know if those time periods are years or months or quarters because we haven't given enough information to know that. But we don't assume those are years unless we have some reason for that, some basis for that assumption. One basis for that assumption would be this. If no time period or compounding period is mentioned, then the default assumption is we're talking about annual interest rates and the period would be equal to 1 year. But if we say, for example, that the interest rate is 12% and we have monthly payments, then we've implied through mentioning monthly payments that our compounding period is 1 month. So we would have 12 months in a year. And so the 12% mentioned was the nominal interest rate, and to get the periodic interest rate, we divide by 12. So without mentioning exactly what the compounding period is, we assume it's a year. And then if it's not, that'll be based on the context of the problem we're dealing with. Okay, well, we're on slide number 28 now. If you want to take a stretch, go ahead. I should have mentioned earlier that it would be good for you to have your textbook handy because I'm going to be jumping into it to show you some tables. So why don't you go get your textbook. If you want to pause for a moment, pause the audio for a moment, go ahead. We're going to start by calculating a future value using our factors and our notation. And this is going to be based on some stuff from the book. So the formula that we've mentioned before for future value is shown there. And that factor that you see there, the 1 plus I to the n, is called the single payment compound amount factor. And what we have are some computations of factors for various interest rates I and number of periods n, and those are put into a table in the back of your book. The notation is shown with three arguments. In the parentheses, you see, in this case, f over p. And what that means is that the factor we're dealing with is a single payment factor where, given p, we're trying to find f. The second argument is I, that's the interest rate, and it's a decimal, it's not a percent. And then N is the number of compounding periods in our problem. Now, our problem may encompass 1 year, it may encompass 5 years, but N is the number of compounding periods in our life of our project. And if you want to set up a problem, for example, to find a future value, you would set it up where you'd say the future value equals the present value times the single payment compound amount factor. And let's go to, then we go to the tables to find what the value of the factor is. Slide number 25 paces you through that. So if we're going to use our tables, the first step of using the table is to find the page that corresponds to the interest rate. So you go back to the back of your book and you find the 6% table. That's step 1. Then you have to find the proper column. In this case, F over P column is the first one. Then you go down to the value of N. The number of periods is on the left side of the page. You go down to N equals 10, and if you look at the F over P column, you see that the factor is 1.791. So if we plug that factor into our formula, where the notation was, then we find that F equals 5,000 times 1.791, or $8,955. So that's the way we're going to do all of our problems, practically all of our problems, with the exception of when we're using an Excel spreadsheet. Slide number 30 shows what we do when we have an Excel spreadsheet to get that same factor. On the top of the Excel spreadsheet, on the menu bar, you'll see an icon that has the letter symbol F over X, or F of X. The F of X icon gets you to a menu of different function libraries, and you want to select the financial function library or menu. Then once you're there, it gives you lots of different types of financial functions to choose, and the one that's equivalent to what we've been dealing with is the FV, or future value function. If you go to FV, and if you click on it, it's going to give you an opportunity to enter 5 different arguments. The rate for Excel is equivalent to I, that's the periodic interest rate. NPER is the number of periods, which is RN, our value for N. Payment, we'll talk about what that's for later. That'll be in chapter 4. But if we're finding the future value of a present sum, then that's 0 for us right now. So PMT argument is 0. PV is present value, or our value for P, the present sum. And then the type equals, in our case, 0. Now let me tell you what that is. Now's as good a time as any. We use the convention in our book, in this course, called the end of period convention, where payments and money coming in is timed at the end of the period. The alternative to that is to use a convention where the cash flows are at the beginning of the period or at the middle of the period. It turns out that most textbooks like ours use the end of period convention. And there's several reasons for that. It makes some sense, and most of all, it makes the equations a lot simpler. So if you're using the end of period convention, then the cash flow is a type 0. So the default is end of period convention. So for our course here, we'll always be using the type 0, the default disbursement of cash flows. Okay, I'm not going to go into any more detail on the Excel spreadsheet input right now, other than to say that you can either put the value in for the arguments on the Excel functions, or you can put the cell address in where on your spreadsheet you have that value stored. So you have two different ways to get that data into the formula. You can also put little formulas in there, but that can be tricky. All right, let's go to slide number 31, and we'll talk about our other lump sum value. If you'll turn to the inside front cover of your textbook, hopefully your textbook's still handy. If you look at the top of that inside cover, you see that we have two single payment formulas there. We have the compound amount factor and we have the present worth factor. We've already covered the compound amount factor, and now we have the present worth factor. And we use the same structure for finding the factors in our tables at the back of the book. So if we want to find the present value of a future amount of $5,000, we can find the P over F column on our 6% table, go down to n time periods. In this case, let's say it's 10, and we can find the factor, multiply it by 5,000, and find the present value. Let's go to slide number 32, and let's find an example of finding the present value of a future sum. We want to find what's the equivalent present value of some amount in the future. So let's say that the future amount is $1,000, and that's 5 years from now, and if the interest rate is 10%, what would be the equivalent present value? Using our notation, we would have that the present sum equals the future sum times the P over F factor for I equals 10, N equals 5. If you go to your 10% table and look for the P over F column, now that's the second column in the table, and you go down to N equals 5, you see that the P over F factor is 0.6209. So $1,000 times 0.6209 is $620.90. So what that means is that $620.90 today is equivalent to $1,000 in 5 years at a 10% interest rate. Okay, well, that ends a very long presentation number 5. In the next presentation, presentation number 6, we'll be picking up on this, but we'll be looking at different types of factors. The single payment factors were covered in chapter 3, and those were the simple ones. And so, anyway, we'll see you in the next presentation. Bye.